Hello, this is Dr. Hanaa Assil, and today we're doing a general review on paper 6, IGCSE Chemistry. So this deals with all the experimental techniques that you need in the IGCSE exam papers. So the basic thing you should know is the names of the apparatus. So let's see the names of the apparatus. Of course, this is called what? This is a test tube, and this is just to put solutions in. This is what? Conical flask, round bottomed flask. This is the kind of flask that we attach to a condenser. You can call it round bottomed flask, or you could just name it flask. This one, of course, is a beaker. Remember, a beaker is not used to measure any volumes. It is just to add solutions in it. What is this? This is a glass rod used for stirring. So when we say we stir the solution using a glass rod, this is, of course, a funnel. We use it for filtration. This is what? Mortar and pestle. The bowl itself is the mortar and the handle is called the pestle. Of course, this is for crushing a solid. What's this? This is a watch glass. Usually we use it to cover a beaker, especially if we're doing something like chromatography. This is to prevent the solvent from evaporating. This, of course, is a crucible and lid, so we use it if we're trying to heat a solid. This is an evaporating dish. The evaporating dish, we usually use it when we're doing crystallization, when we're trying to heat a solution to point of crystallization. We do that in an evaporating dish. This, of course, is a balance to get the mass of the reactants. And to measure the mass, you can have a question like this, where he gives you readings and you're supposed to fill out the table. Of course, usually this is in 1 decimal place. I want to remind you that when you're filling out any table, you should not put units inside the table. So don't write 86.0 gram, 84.4 gram, 84.1 gram. You don't include units inside the table. The units are written at the top, and that's it. Okay, what's this? Bunsen burner, of course, to heat any solution or any reaction. This is a dropper. If we say add 3 drops of indicator, for example, or any solution, we use a dropper. This is, of course, what? This is a measuring cylinder. Remember, a measuring cylinder has graduations. It is used to measure volumes of liquids, but it is not accurate. So usually he asks you, what is the advantage of using a measuring cylinder? The advantage is that it is fast or quick. But what is the disadvantage of using a measuring cylinder? In that it is not accurate. Okay, this is very similar to the measuring cylinder, but it has no graduations. This is called a gas jar. So if we have no graduations, it is called a gas jar. The same thing, but with graduations, then that would be called a measuring cylinder. This is, of course, a burette. It is something that has graduations and a tap. This, of course, measures volumes of liquids very accurately, and it can measure any kind of volume, 21.0, 21.3, 25, and so on. Okay, use the burette readings to record readings in the table. So he gives you burette readings. You want, in most cases, he will ask you to fill out the table. What is the final? Please notice which one is final and which one is initial. This is a common mistake. The final is the one on the right. So the final, for example, remember that a burette is read from up to down, from the small number to the big number. So this is actually 29.1. The initial is 24.0. If he says the difference, then you just subtract. Okay, what's this? This is a pipette. Remember that the pipette also measures volumes of liquids very accurately, but it measures only a specific volume. So for example, it will measure 25.0 and any multiples of that. So I can use it to measure 50 because I can use it twice, or I can use it to measure 75. So I can use it 3 times. But I cannot use it to measure anything in between. So I cannot use it to measure, for example, 30 centimeter cubed or 40 centimeter cubed because there are no graduations. Okay, so for example, in this kind of question, he says label these apparatus. Of course, the one on the right has graduations and a tap, so it is burette. The one in the middle is now a pipette. This is what we use during titration to add a specific amount of solution to the conical flask. Okay, here he's comparing reading a burette with reading a measuring cylinder. We read either of them from the small number to the big number. So the burette, for example, we're going to read it, it is 27 point something. So that is 27.8. Can you see that? The measuring cylinder on the right, it's from 40 to 50. So this is 40 something. So this is 44, for example. So my answer here is B. Okay, this is called what? This is a tripod stand. Sometimes they say just tripod, but actually it should be tripod stand. This is what we put our flask on when we're heating. This is a spatula. The spatula, of course, is used to add solid. So when I say I add solid from a bottle, I use a spatula. So that one is a spatula. The other one here is a glass rod, and of course that is a tripod stand. Okay, what is this? This is a stand and clamp. Can you see which one is the stand and which one is the clamp? So this is used to hold anything. For example, it's used to hold a burette. Okay, thermometer, of course, to measure temperature. So when we do distillation, we're going to have a thermometer in the flask. This is a gas syringe. We use it to measure volumes of gases. So if I have a gas given off and I want to measure its volume accurately, I use a gas syringe. So how do we read the gas syringe? At time 0, the plunger is all the way in, so the total volume there is actually 0. But then as the gas goes up and fills the gas syringe, the plunger moves backward to the right. So this is now 45. This would be 48. Of course, again, please do not include units inside the table. Don't write 48 centimeter cubed inside the table. It's already written at the top. Okay, what is this? This is tongs. And the tongs, of course, we use it to hold something that is hot, or we use it, for example, when we're burning magnesium or something, we can use it to hold that. Okay, this one is very similar to tongues, but this is used to hold a test tube. So this is a test tube holder. This, of course, is a condenser. We use it in simple distillation or in fractional distillation. And that thing that we put the flask on is called the wire gauze. So this is what we put, whatever we're heating, it stands on the wire gauze. This is a delivery tube, just connects from one part of the apparatus to another. These two are types of funnels that are put on a flask. So one of them has no tap, the other one has a tap. So the one without a tap is called the Thistle funnel. The one with a tap is a dropping funnel. Remember, both of them do not have graduations. So the dropping funnel is very similar to a burette. It has a tap, but no graduation, so it is called a dropping funnel. While that one on top here would be what? It would be a Thistle funnel. In review of all of this was called flask, this was wire gauze, and this Bunsen burner, this is tripod stand, this is delivery tube. This is what? A gas jar, of course, because it doesn't have any graduations. Now, what is this at the bottom in which we have the water in it? This is a sort of beaker. It's a wide beaker, but we call it a trough. So remember that a big beaker or a wide beaker is called a trough. Okay, so safety precautions in the lab. Remember, if he says suggest a safety precaution, well, we take a look at the question. What is he using? If he's using ethanol, you should remember that ethanol is a flammable liquid. So our safety precaution would be heat in a hot water bath. So when I heat the ethanol, I do not expose the ethanol to an open flame. I put it in the test tube and the test tube inside a beaker with water. This is called a hot water bath. So my precaution is heat in a hot water bath. Now, if it's not using ethanol, I take a look again. Is it using any gases? So whether gases are reactants or gases are produced, I tell him do the experiment in a fume cupboard. A fume cupboard is this kind of cupboard with a door where I can put everything inside and close the door, so this does not allow the person to inhale any of the gases. So any experiment that has gases and he says suggest a safety precaution, do the experiment in a fume cupboard. If not, then I see, are we heating something? Then hold the hot objects with tongues, of course, to avoid burning your hand. Nothing of that, then I can say wear safety glasses, especially if I am heating something or I have something that is bubbling. If I'm using acids or bases, then you should know that an acid and a base are corrosive. Corrosive means they harm the skin. So the precaution would be wear gloves. So you have to remember that when using acids or bases, what is the hazard? Remember, the word hazard means what is dangerous about it is that these are corrosive substances or corrosive solutions, so the precaution would be wear gloves. What if he says suggest how to improve the accuracy of an experiment? Well, if we're doing an experiment, he's measuring something, I will tell him repeat each reading 3 times and obtain the average. Why? Because it is more accurate. Or if he's measuring liquids, and if he says he measured the liquids using a measuring cylinder, I tell him no, we should not use a measuring cylinder, use a burette instead of a measuring cylinder because it is more accurate to measure volumes of liquids. If not, then I look, is he measuring volume of gases? Well, he should be using a gas syringe. So if he's using anything else like a gas jar or measuring cylinder, then I will tell him use a gas syringe to measure the volume of the gas because that is more accurate. Are we all following? What if he says he wants to dry a solid? Well, I prepared a salt of any kind and he wants it dry. The basic thing will be dry between filter papers. We do that because we don't want to cause any decomposition of the salt. Sometimes he uses a desiccator. A desiccator is this kind of apparatus where we put a drying agent such as anhydrous calcium chloride. So if he has in the experiment, he's using anhydrous calcium chloride and he asks why are we using anhydrous calcium chloride, it is probably to dry the solid or to dry the gas or to remove water. Remember, we never say heat the crystals in an oven when we want to dry it because this would cause the decomposition of the substance, especially if I'm trying to prepare a hydrated salt. Remember, a hydrated salt means a solid that has water of crystallization in it. That means when it forms crystals, it takes water with the crystals. So if I put that in an oven, the crystals will decompose or I will lose the water of crystallization. Okay, what if he's saying when we want to dry a gas? Or he says he passed the gas through concentrated sulfuric acid. Why do you think he passed the gas through concentrated sulfuric acid? It is probably to dry the gas or to remove water. Another method to dry the gas could be to pass it through a U-tube that contains either anhydrous calcium chloride or silica gel. Anhydrous calcium chloride or silica gel are substances that suck up the water or absorb the water in the gas. So why are we passing it through this? To remove the water or to dry the gas. Okay, these are hazard labels. You should be familiar with them. In the O level, sometimes he doesn't ask very much about it, but you should be familiar with this, especially the one that says toxic. Can you see the one with the skull? That's the one that says toxic. Flammable, corrosive. We said corrosive. We have it on a bottle of acid, for example. It will have corrosive because that harms the skin. Try to be familiar with these. Okay, when drawing a graph, he says, draw a graph. First of all, you draw the points with small x's or dots with circles. Please do not draw a graph with just a dot, because if it is not clear to the examiner, then you do not get grades. So, plotting a graph, you plot it with small x's or with a dot with a small circle. Now, when we have a point that is away from the curve, this is called an anomalous result. So that means something went wrong with that result. It's not correct. So I do not include it. I do not say like this. I don't draw the graph so that it is a weird curve like this. It has to be a smooth curve. If a point is away from it, I ignore it. Okay. Sometimes he says, okay, in the tests in paper 6, at the end of the paper, there are tables where he says, I have a solid and we're doing tests on the solid. The first thing he will tell you is it colored or is it a white solid? So if it is colored, he says it's green or pink or yellow or whatever, that tells you it has a transition metal. But if he says it is just a white solid, then that means there is no transition metal. Remember, if there is no transition metal, if it's a solid, we say it is white. If it's a solution, we say it is colorless. Colorless solution, white solids. We don't say colorless solid. Okay? And then sometimes he says he heated the solid and condensation forms at the top of the tube. If he says he heated the solid and condensation forms at the top of the tube, that tells you that the solid was a hydrated salt. That means that the crystals had water of crystallization in it. So when you heated it, the water came out. Now, how do we collect gases? Well, that depends on what type of gas. If the gas is not soluble in water, then the easiest method would be to collect the gas over water. So I can use this method to collect a gas if I'm trying to collect gases like oxygen or hydrogen because they are insoluble in water. But if the gas is soluble in water, I cannot do that. So I have to collect it either by upward delivery or downward delivery. Now, if the gas is lighter than air, and you have to remember that ammonia has lower density than air, or it is lighter than air, then how do we collect it? We collect it by upward delivery. The delivery tube goes up. If I'm talking about a gas like carbon dioxide is heavier than air, I collect it by downward delivery. But in all of these cases, I'm not measuring volume. If he wants the volume of the gas, then I have to tell him to collect it in a gas syringe in order to determine the volume of the gas. Okay. In other questions, he would say, for example, he has a delivery tube going into water and we're heating that tube that has the liquid alkane and broken tile and things like that. Now, when I'm heating this tube with the delivery tube in the water, once I have finished, I have to do something. I have to remove the delivery tube from the water before I stop heating. So the delivery tube must be removed before the heating is stopped. This is to prevent any back suction of water into the hot tube, which would break it. Now, if I remove the heat with all the setup the same with the delivery tube inside the water, then the gas in the test tube will cool and it will suck up water back into the hot tube, and that means the hot tube will break. Okay, in any experiment, why do we use a cotton wool? Well, we could use a cotton wool for one of three reasons. If I have a tube like this, like the previous experiment, and I want to heat liquid alkane or water or ethanol or whatever, if I have a liquid and I have the tube horizontal like this, I have to put the liquid in a mineral wool or cotton wool. The purpose of that is to hold the liquid so that the liquid does not seep out of the test tube. Or in other cases, it is to prevent solids from passing through the apparatus. So I have a test tube with solids that could go through the apparatus. I don't want the solids to go through apparatus, so I put cotton wool around it to hold the solids. Or when we're doing experiments on rates, we put a cotton wool at the mouth of the flask. This is to prevent loss of solution by splashing, because in these experiments, if it is giving out a gas, I need to allow the gas to escape, but at the same time I need to prevent loss of solution by splashing. A suction pump. If we have a setup like this and he says I have a suction pump, what is the function of the suction pump? It is used to suck the gases through the apparatus. So for example, I'm burning a fuel. I want the gases that come out of the burning to go through into the test tube. So I use a suction pump to suck the gases through the apparatus. An airlock. When we're doing fermentation, I don't want oxygen to go in, but I want the carbon dioxide that is formed inside the reaction to go out. So I use an airlock. So the airlock allows the gases to come out of the flask, but does not allow air to enter into the flask. When we're doing measurements of temperatures now, if we're talking about an exothermic reaction or an endothermic reaction, the temperature will either rise or it will fall. What happens is at the beginning, this reaction starts and the temperature, for example, starts to go down. If it goes down, you know that it's endothermic. If it goes up, you know that it's exothermic. But then if I leave the reaction and come back 1 hour later, you should realize that after that, it will go back to the original temperature that it started with, the original room temperature that was there at the beginning of the reaction. So if he says after 1 hour, what is the temperature? I look at the table of temperatures and I see what was it at the very beginning of the experiment. That's what it will go back to at the end of the experiment. Again, if we're doing an experiment that involves measurement of temperature, you have to remember that we do the experiment in something called a polystyrene cup, and it should have a lid. So if it doesn't have a lid, I should tell him it should have a lid. So the polystyrene cup with the lid is used in experiments in which I'm measuring temperature. This is because the polystyrene is an insulator, so there will be less loss of heat to the surroundings. Please remember all of these things are very important. How do I read a stopwatch? He already would tell me that the ones inside are minutes and the ones outside are seconds. So this, for example, is reading 1 minute and 26 seconds, but usually you need to fill a table in which you need to put it in seconds. So of course, 1 minute is 60 seconds plus the 26. So this would be a total of 86 seconds that I would record in the table. So a table like this, for example, can you tell what the time should be? Well, the first one has 2 minutes and a few seconds, that is 128 seconds. The second one has only 58 seconds. The third one has 27 seconds. Again, please do not write seconds inside the table. Okay, these are things that you should be familiar with. your reading is either reliable or valid or accurate or precise or anomalous. Reliable means if I repeat the experiment, it will give me the same result. So we say the reading is reliable. Valid means I am measuring what I'm supposed to measure. So it could be a correct reading, but that's not what I'm supposed to measure. If it is, then it is valid. An accurate reading means it is the same as what it should be, the same as the true reading. Precision, precise means it is the same reading that is obtained under the same conditions. An anomalous result, and this is the one that's most important, you should remember that anomalous means it is wrong. There is something wrong about it. It does not fit the curve, or it is away from the curve. Okay, how do we separate mixtures? If I have something that is insoluble, then I do that by filtration. So I tell him, filter through filter paper and funnel, and please be familiar with the drawing. Sometimes he asks you to draw the diagram for the apparatus used in filtration. So, for example, you know that at the end of paper 6, there are experiments that you're supposed to explain. So this is an example. He says beach sand is a mixture of sand and broken shells that are made of calcium carbonate. Now, calcium carbonate reacts with dilute hydrochloric acid to form a solution of calcium chloride. That means that calcium carbonate is soluble in acid. Plan an investigation to find out the percentage of shell material, and he says that the shells are the calcium carbonate, in a given sample of beach sand. So that means I have a mixture of sand and calcium carbonate, and he's telling me that the calcium carbonate dissolves in acid. The sand, of course, does not. How do I get the percent calcium carbonate in the sample? Well, if he wants percent of something, then the very first thing you should do is weigh a certain mass using a balance. Of course, if I'm explaining all of this, it's very important to tell him the apparatus that he will be using. So, and then when you explain this, it is as if you're explaining it to someone who has no idea about chemistry, and you have to go one by one, tell him exactly what he's supposed to do. So the first thing I should do is weigh 10 grams, for example, of beach sand using a balance. Then I put it into a beaker. He said that the carbonate will dissolve in acid, the sand does not. So I add excess of the acid, stir with a glass rod. The calcium carbonate will dissolve, bubbles of carbon dioxide gas are given off, and then I should filter through filter paper and funnel. The sand is collected as residue. He wants what? He wants to know how much calcium carbonate, but the calcium carbonate has dissolved. So what I will do is I will weigh the sand that is residue. So dry the residue and weigh, and then subtract from the original mass. So if I had 10 grams of the total, I end up with something of the sand, then the difference is the amount of calcium carbonate, and then I can calculate percentage, and I can, if I want to, I can go on and tell him how to calculate the percentage. Of course, the percentage is the mass of the carbonate over the total times 100. Okay, this is another example of the investigations that we should be explaining. So he's saying copper oxide and carbon are both black solids. Copper oxide reacts with sulfuric acid. Carbon does not react. You are given a mixture of copper oxide and carbon, access to dilute sulfuric acid, plan an experiment to investigate the percentage of copper oxide. So this is basically the same experiment. So I'm going to weigh, of course, 10 grams of the mixture using a balance, put the mixture into a beaker, add acid, stir with a glass rod, filter through filter paper and funnel, wash the residue with a few drops of distilled water. Of course, the residue here now is carbon. Dry the residue between filter papers, weigh using a balance, subtract from the original mass, and calculate the percentage. So this is basically the same experiment as the previous one. Now, here this one says a toothpaste contains sodium fluoride, calcium carbonate, silica, mint flavor. Then he says sodium fluoride and the mint flavoring are soluble in water. Calcium carbonate and silica are insoluble in water. Calcium carbonate reacts with dilute hydrochloric acid to form the soluble salt calcium chloride. That means calcium carbonate will dissolve in acid. Plan an investigation to find the percentage by mass of silica. Again, what should we do? First, we weigh 5 grams of the toothpaste. You can say 5 grams, 10 grams, whatever you want, using balance. Then put into a beaker, add excess dilute hydrochloric acid, stir with a glass rod until no more bubbles of gas are given off. Then filter through filter paper and funnel. So in this case, everything has dissolved except the silica. So the silica is collected as residue. Wash the silica with a few drops of distilled water, dry between filter papers, and weigh. And of course, we will calculate the percentage of silica in the toothpaste. You can also tell him exactly how to calculate. So in this case, we can say, for example, it will be the mass of silica over the initial mass times 100. This is another example of this kind of questions. Which is the more pure, limestone or marble? So he says calcium carbonate is found in limestone and in marble. All carbonates react with hydrochloric acid to form chlorides. Calcium carbonate is insoluble, but calcium chloride is soluble. That means if I have the calcium carbonate, I add the acid, it will dissolve. Most impurities in limestone and marble are not soluble. So plan an experiment to find out which of the limestone and marble contain the most insoluble impurities. Again, most means I need to weigh at the beginning, weigh 10 grams, for example, of limestone using a balance, put into a beaker, add excess dilute HCl, stir using a glass rod until no more bubbles of gas are given off. That means all the calcium carbonate has dissolved, only the impurities did not dissolve. So filter through filter paper and funnel. The impurities are now residue. Wash the residue with a few drops of distilled water, dry between filter papers, weigh the residue using a balance. And then we're going to do the same with the same mass. You have to indicate that I will use the same mass. If we're comparing between limestone and marble, I have to use the same mass. The one that has more residue has more impurities. So these are basically very similar. Please adjust your answer according to what he's asking for. Then the other kind of separation is crystallization. Remember, when do we do crystallization? If I have a solution and I want the salt. So I have a solution. I want the salt. How do I get that? Heat to point of crystallization. Heat to point of crystallization means I'm trying to get a saturated solution. Now cool, I have to cool after heating to form crystals. Then I filter the crystals through filter paper and funnel. Then I dry the crystals between filter papers. So how do I know if I have reached the point of crystallization? Usually crystals form on the edge. Or I could tell him insert a glass rod and remove it. Crystals should form on the tip of the glass. That is how I know if I have reached point of crystallization or not. And at that point, what I have is a saturated solution. So if he says, what do I mean by a saturated solution? It is one in which no more solid can dissolve at a certain temperature. Remember, at different temperatures, there are different amounts that can dissolve. So this is an investigation. He says ethane dioic acid dihydrate is a white crystalline solid. This acid is water soluble. It is found in rhubarb leaves. Plan an investigation to obtain crystals of this acid from some leaves. You are provided with common laboratory apparatus, water, and sand. Remember, if he gives you things, you have to use all of them. Now, what are we doing first? Why does he give me sand? Because when I crush the leaves, I need to crush them with sand. The presence of the sand helps to crush the leaves. And then I can put it into a beaker and stir. So the first thing I need to do is crush the leaves with some sand in a mortar and pestle. Please do not forget to mention the apparatus you're using. Then I'm going to put it into a beaker, add water, stir with a glass rod, and then I'm going to filter through filter paper and funnel in order to remove the remains of the leaves and the sand and all that. So what I want actually is the filtrate. Now I heat the filtrate to point of crystallization, cool, filter the crystals, and that is how we get the crystals of something out of leaves. Here he's saying a mixture contains 3 solid compounds: copper sulfate, cetyl alcohol, silicon dioxide. And he's telling me that copper sulfate dissolves in water, the other two do not. And then cetyl alcohol dissolves in propanone, the other two do not. So plan a method to obtain a pure sample of each of the 3 solids, copper sulfate, cetyl alcohol, and silicon dioxide, from the mixture. So what do? Put the mixture into a beaker. Add water and stir with a glass rod. Of course, if I add water, which one will dissolve? Copper sulfate dissolves. Filter through filter paper and funnel. That means that the other two would be in the filter paper and my copper sulfate solution is in the filtrate. So heat the filtrate to point of crystallization, cool, filter the crystals, wash with a few drops of distilled water, dry between filter papers. That will obtain copper sulfate crystals. Then I will take the residue that was in the funnel and that contains the cetyl alcohol and the silicon dioxide. I put it into a beaker. I add the other solvent now, the propanone. When I add the propanone, it is the cetyl alcohol that would dissolve. So cetyl alcohol dissolves, filter through filter paper and funnel. The silicon dioxide is now residue. Wash the residue with distilled water, dry between filter papers to obtain silicon dioxide. And then the filtrate from that, I put into an evaporating dish. The propanone evaporates, leaving the cetyl alcohol. Are we following? Okay, this is another one. He says potassium chloride is a salt that dissolves in water. The solubility of a salt is the mass in grams of the salt that dissolves in 100 centimeter cubed of water at a particular temperature. Plan an investigation to determine the solubility of potassium chloride in water at 40 degrees Celsius. What do? I want how much will dissolve in 100 centimeter cubed of water. So I put the 100 centimeter cubed of water in a beaker using a measuring cylinder. He wants it at 40, so I heat it to 40. Then I weigh a certain amount, 100 grams, for example, a very big amount. So 100 grams of potassium chloride using a balance. I add to the water and stir. Of course, some of it will dissolve, some of it will not. Now I filter, dry the residue between filter papers, weigh using a balance, and I subtract from the original mass in order to know how much has actually dissolved. Okay? Now, another method of separation is simple distillation. Now, when do we use simple distillation? We use simple distillation if we have a solution and I want the water. Remember, when we had a solution and I want the salt, I do crystallization. But if I want the water, then I do simple distillation. Remember that the thermometer determines the boiling point of the liquid. The liquid has lower, the water, for example, has lower boiling point than the salt that is dissolved in it. So it will boil first, go into the condenser. If he says what is the function of the condenser, it is to cool and condense the vapor. To cool and condense the vapor, and I get the pure liquid collected in the conical flask. So here he's saying, describe how simple distillation is used to separate water from an aqueous solution of sodium sulfate. So he has a solution, he wants the water. In your answer, refer to the apparatus used, changes in state, differences in boiling point. So this, of course, is simple distillation. So you should be able to draw that. And then how do we explain it? We say put the solution into a flask connected to a condenser. Heat the solution in the flask. Water has lower boiling point than sodium sulfate, so it boils first, turns into vapor. The vapor goes into the condenser where it cools and condenses to form pure water and is collected in a receiving flask. This is how we explain simple distillation. Now, the other method of separation is fractional distillation, and the difference here is that here we have that part that is called fractionating column. Now, when do we use fractional distillation? This is to separate a mixture of liquids based on the difference in boiling point. So the one that has lower boiling point will boil first and will be collected into a beaker. So that would be what we call the first fraction. So these are liquids at a certain temperature, and then the temperature rises. How do I know if I have collected everything? So long as something is being collected, the temperature remains constant in the thermometer. Once I have collected the first fraction, then the temperature starts to rise until we reach the boiling point of the next one, and then that boils and is cooled and condensed in the condenser. So here, for example, you should realize that that is a thermometer. That is called a fractionating column, and that, of course, is a condenser. Now, which liquid will be collected first? Well, he says ethanoic acid has a certain boiling point. Chloroethanoic acid has another boiling point. The one that has lower boiling point is the one that is collected first. So in this case, the ethanoic acid would be collected first because it has a lower boiling point. How would the teacher know when all the liquid has been collected? Remember we said if we have one of the liquids coming out, then the temperature remains constant. Once all the liquid has been collected, then the temperature will start to rise. Then he says, suggest why small glass beads are used in the fractionating column instead of large glass beads. Always remember that something that is smaller would have larger surface. This is a typical question about the separation technique. So he has the options A, B, C, D, and he's saying which of these should I use to get pure water from seawater. Remember we said if we have a mixture and I want the water, then I use simple distillation. If I want ethanol from a mixture of ethanol and water, these are a mixture of two liquids, then I will use fractional distillation. Calcium carbonate from a mixture of calcium carbonate and water. Again, calcium carbonate is something that does not dissolve in water. So to separate it from water, I use filtration. Now, what about copper sulfate 5 water solid from copper sulfate aqueous? That means I'm getting crystals from a solution. So, of course, that is crystallization. How do we separate gases? If he has a mixture of gases, I separate it by diffusion. So we have a porous tube. The tube in the middle here has tiny little holes, so it's called a porous tube. We allow the mixture of gases to flow near the porous tube. The gas with lighter particles, lower molecular mass, will diffuse faster into the porous tube. So that tube in the middle would have, for example, more oxygen than the tube outside, and the one outside I will have the chlorine left in it. So this separates a mixture of gases. Paper chromatography is used to separate a mixture of dyes. So I could have a spot of ink or food coloring, or a mixture of amino acids, or a mixture of sugars. And we try to separate them to know how many or which ones do we have. Now, once we have many of them, I want to know if sample A contains 1 or 2 or 3. So I put all of them on the same line, and if they go up the same height, then they are present. So for example, in this chromatogram, A contains sample 1, but not 2 or 3. Or I could calculate the RF value of the spot. Remember that the RF value of the spot is the distance traveled by the spot over the distance traveled by the solvent. So for example, in this diagram, remember what are the parts of the chromatogram. The origin line or the baseline, we said, should be drawn in pencil so that it does not dissolve in the solvent. The solvent is the one at the bottom. Remember that the solvent must be below the origin line or the baseline so that the spots do not dissolve in the solvent. The one on top there is the solvent front. So this is where the solvent went up, and that of course is the chromatography paper. So this is an example of an experiment. He says an orange drink may contain artificial colors E110 and E129. Plan an investigation to determine the presence of these artificial colors in a sample of orange drink. So again, if I want to know if my sample contains something, what I do is put a spot of the orange drink next to a spot of E110 and E129 on a baseline near the bottom of a rectangular filter paper or chromatography paper. And then I tell him, remember, you're explaining in detail in the correct order. So I put the spots on the baseline. And then I put the paper into a beaker containing a very small amount of water. And then allow the water to move up the paper. And then you have to tell him how is he going to know whether it has it or not if the orange drink has spots the same height as the artificial colorings, then they are. Remember that sometimes we do chromatography of something that does not have a color. So for example, if he's saying we do chromatography of amino acids or sugars, they do not have a color, I have to remember to tell him that we will be, in that case, we will be spraying the chromatogram with a substance called locating agent. This gives the spots color and makes it visible. Okay, so this will be the end of the first part of this review. I don't want to make it too long, so there will be a part 2 to this. Please listen to the second part in order to review the rest of the topics that you need to know for paper 6 or for any practical experimental techniques that are needed in the question papers for IGCSE. Thank you for listening. Please listen to the next part of this review.